Okay, moving on. So we saw that Dagger is a pretty effective algorithm, but it has a pretty strong assumption to it, right? Which was?
An injective demonstrator.
Right, that we have the demonstrator along with us to the right, and we can always ask the demonstrator what should we do in different states. So let's drop that assumption. So meaning that we cannot use Dagger. But, so again, we have an offline set of demonstrations. And we would like to do something better than supervised learning, than behavioral cloning. So let's look at several solutions for that. First of all, let's look at inverse reinforcement learning. So we don't assume to have an interactive demonstrator. We only have access to an offline set of demonstrated trajectories. As we said, behavioral cloning is not a robust approach. It suffers from overfitting. We know what to do in the observed states, but we cannot generalize well to other states. How can we learn to mimic the demonstrator in a general way? So this is where inverse RL comes into play. We'll try to learn the demonstrator's objective, or the reward function, what motivates. So we're not trying to learn what specific actions the demonstrator is doing in specific states, but actually what motivates those actions. Right? Once we learn the motivation, then we hope to be more robust even in states that we did not see during the offline demonstration set. But in any case, once we obtain or train such a reward function, or learn such a reward function, then we reduce the imitation learning problem into a reinforcement learning problem, right? We can use a reinforcement learning algorithm to solve it. Okay, so let's define inverse reinforcement learning at the highest level before we go into specific solutions. So we assume a set of offline demonstrations, so we have several trajectories that are sampled from our demonstrator, but that's it, we cannot obtain more data. Okay, so this is just offline demonstrations. Next, we would like to learn a reward function, specifically if we do inverse reinforcement learning. So we're trying to learn a reward function that is used by the demonstrator, or we believe to be the reward function that the demonstrator is optimizing. And this reward function should be a unique one, such that for any policy that we can train, the reward obtained by trajectories given by the policy are the highest possible reward. So we're trying to train a reward function such that the trajectories obtained by the demonstrator are the highest, the one with the highest return. That is, this is the reward function where our demonstrator is acting optimally with respect to, right? So for that reward function, the demonstrator will return the highest expected reward with respect to any other policy. And we're hoping to have a policy that returns the same reward, sum of rewards, but in any case, our demonstrator is optimal with respect to that reward function. So we'll have to add an assumption here, of course, that is that such a reward function actually exists. That is, the demonstrator is optimal in some sense. It has some objective. So this is also goes back to the definition of a rational agent, which actually didn't cover in this course. You should have covered that in the Intro to AI course. We need to assume that our demonstrator is a rational agent in this case, so it is optimized as some reward function. And then our output in inverse reinforcement learning would be some approximation of the demonstrator policy that is trained using reinforcement learning with the reward function RD. How do we do that? So this is a process where we take our demonstration trajectories, we train or we derive some reward function, then we train some policies, our policy approximator, to optimize the reward function. Then we compare our policy, the reward obtained by our policy and those obtained by the demonstrator under the same reward function. And if we see that our policy, well, our optimal policy obtained more reward compared to the demonstrator, then we change, we update our reward function such that will not be the case, such that our demonstrator would be optimal under that reward function. But it's not always, so the engine of this process would be to update or to set the reward function, right? This is the hard point. We know how to do reinforcement learning. We probably know how to compare two rewards, two sets of rewards. But we really need to decide how are we going to do the update stage? How do we set and update our reward function? And this is not necessarily an easy job, right? For instance, let's say you don't have any knowledge of chess rules. Maybe that's the case, I don't know. But if you assume not to have any such knowledge, I can ask you what reward function results in the white player's policy. Right, so the white player here moves its pieces in some way. And if I would ask you, hey, come up with a reward function that results in this behavior, well, you can see that that's not very easy to do, right? Because there's a lot of ambiguity here. Moreover, there's many reward functions that can fit a specific behavior. And many of these rewards, in many cases, can be degenerate solutions. Actually, there is a degenerate solution that might fit with this constraint always, which would be simply assign zeros, right? If all of the rewards are zeros, the reward function always returns zeros, this constraint will hold. But that will be a degenerate solution. So let's try to find or define our first algorithm to actually do effective inverse reinforcement learning. So our first solution will define the reward function as a linear approximator, or as a linear function. It's not when we're approximating the true reward function, but let's say that the reward function that we are setting is a linear approximator. What does it mean? It means that we have a vector of weights and the state features, right? And we do a dot product between these two vectors. Okay, so let's look at one solution to defining the reward function unambiguously, or a solution that can provide us with a solution in practice, one algorithm to do inverse reinforcement learning. So in this solution, we'll define our reward function. This is the reward function that we are learning, right? We'll define it as a linear function, right? Where we can tune the W vector. This is just a vector of weights. And the reward is a simple dot product between the weight vector and the state features vector. So W is the set of weights that we can tune, and F is the state of state features, the vector of state features. Okay, if we consider the reward function as a linear function, then we can rewrite the expected sum of discounted reward as follows. So instead of the reward function, we'll simply write it out as a linear combination of the weight vector and the state features. The weight vector, of course, is not dependent on the time step or in a specific state in a specific time step, so we can take it outside of the expected value, right? And then we have the weight vector, the dot product between the weight vector and the expected sum of discounted features over all time steps, right? I mean, it sounds a bit weird, but that's what we get. This is exactly what we get. So the sum of discounted feature values, right, vector. Okay, so let's just, instead of rewriting this value over and over again, we'll define it, we'll use the notation mu of pi. Mu of pi is the discounted summation of state features.
Expected.
Expected, right, yeah, it's the expected sum of discounted state features. Oh, right, it's written just here. So, and it is a vector, of course, because we have several dimensions of the state features. So now we can rewrite our constraint, our main constraint in inverse reinforcement learning, telling us that, well, the reward for our demonstrator must be always, our demonstrator is optimal with respect to this reward function, so it should always get high rewards compared to any other policy. Or the same reward if you actually have a policy that perfectly imitates the demonstrator. Okay, so we can rewrite our constraint as follows, right, just here, as W as the vector W times mu of pi d, and that must be greater or equal to W d multiplied by dot product mu of pi for any pi. And now we can solve WD as an optimization problem, right? And how do we define that? We define it as follows. We will try to maximize some delta, and this is important, so this maximization of delta, so what is the delta? The delta is the difference between the dot product W mu pi d and W mu pi, whatever with the policy that we're trying to solve. And we'll add here this delta term. So this means that not only are we trying to enforce this constraint, as we said before, yeah, this can be easily enforced by setting W to zeros, right? And sure, we have this constraint. But not only are we trying to enforce this constraint, but we're trying to actually have maximum separation between the two. That is, we're trying to somehow maximize the difference or maximize the reward obtained by our demonstrator compared to the reward obtained by our trained policy, right? So to differentiate them as much as possible. And this is indeed the maximization process that we're trying to solve under this constraint. And we also try to bound the vector, the set of the L2 norm of our W vector to be lower or equal to 1. This is so this is specific when we assume that all state features are valued from the range 0, 1. Then if we add that bound, this will allow us to ensure that the reward are all bounded by 1, and this is important for theoretical guarantees. So you won't be able to just inflate this value by inflating the W vector. Okay, so this is actually a very important constraint that must be added. What is the problem with this constraint?
That it's non-linear.
Non-linear, uh-oh. So we can solve this optimization problem with a linear program, which is a shame, right? A linear program is actually very efficient, but we cannot do that here. So instead we solve this optimization problem with a quadratic program, and this is indeed what was suggested in the Abil and Nang ICML paper from 2004. So for each iteration, we sample trajectory I-1 from pi I-1 from our previous policy, and then we compute our new approximation of the reward function. This is the reward function optimized by our demonstrator by solving the quadratic program, exactly this quadratic program. And then we train the new policy, our new policy, using reinforcement learning algorithms on the new reward function, on the reward function that we just got. We stop this process once the difference in the reward that obtained by our trained policy and the demonstrator policy is smaller than some epsilon that we define, right, as a hyperparameter. Yeah, question?
So the reward learned satisfies this constraint that you mentioned that the demonstrator is optimal. Mm-hmm. But is there any guarantee provided that this reward does reflect the true objective, or does it just satisfy this constraint?
So not necessarily, right? Not necessarily. this is very sensitive to the features that are defined in the state space, right? It might be informative or less informative, and also it's impacted by the approximation limitations of the policy that you're training, right? Okay, so this procedure, though, does, so there were some convergence guarantees for this process that are presented in the paper that I cite here. We won't go over the derivation, I'll just give you the bottom line. So this process is guaranteed to terminate terminate meaning that the termination, the stop criterion is accomplished, right? And the process stops. It is guaranteed to terminate after an order of k over, well, after this expression, I won't read it out, right, but it's provided here. After these many iterations of this process, in this case, k is the number of state features, right? So if you have more state features, this will be a slower process. And this guarantee only applies for linear reward approximation. Well, actually, this definition is only valid for a linear reward approximation.